Quantum computers have become part of our reality, and today they are used to solve a wide variety of practical problems. They do this quite efficiently and are distinguished by their intelligence or perhaps even ingenuity. But if you open most popular science articles on this topic, you'll only find information about how great it is that quantum computers exist. But what exactly is going on inside the mind of a quantum computer? How does it work in such a way that it manages to outperform conventional computers? And what exactly are quantum computations? In order for us to understand quantum computations, which are at the core of any quantum system, we absolutely need to grasp at least three fundamental or basic concepts of quantum physics. Of course, what interests us are quantum superposition, the observer effect, and quantum entanglement. So, how do we bring all of this together, and for what purpose? Well, perhaps it's worth starting by saying that, in and of itself, a quantum computer is not that different from a regular computer. It uses the same kind of electronics. But there is one fundamental difference that makes this system fundamentally distinct. And this difference lies in the fact that there are qubits, and qubits are things that essentially make it possible to implement quantum effects in practice. But perhaps I'm getting ahead of myself. It's better to start with the strange phenomena of quantum physics. In the ordinary world, we have all sorts of objects, all kinds of physical bodies, and we're used to the fact that any physical object can be touched, that every physical object has a certain position that can be specified by coordinates. It has certain characteristics, and all of this, let's say, can be directly and materially analyzed. And even at this stage, the fundamental differences between the quantum world and the ordinary world begin to appear. The quantum world doesn't have anything definite. If an ordinary object in the material world at the macro level has size, position, and other properties, then a quantum system, a quantum object, does not have such properties. A quantum particle, a quantum object, has a range of probable properties which is described by a probability density distribution. This effect is called quantum superposition. Quantum superposition means that an object possesses all possible probable properties at the same time. Alright, if quantum objects exist in all possible states and can simultaneously have all the probable properties associated with them, then we should probably see millions of possibilities around us. But this is where a second effect comes to our aid, which we will discuss. This is the observer effect, or the process of measurement. When a quantum system enters the real world, it begins to interact with this world. Here it's useful to recall Young's experiment about how, in fact, it was discovered that light is both a wave and a particle at the same time. And how did we even come to understand that objects can have such strange behavior? The logic is that when we interact with a quantum particle using some detector or measure it, this quantum particle takes on a form that is understandable to us. It's as if it emerges from the world of probabilities and enters the macroscopic world, where it becomes a real macroscopic object. This is very difficult to understand and hard to imagine. It's as if you have some kind of box you put your hand in and one of the possible outcomes is pulled out. For quantum computing, it's enough for us that there is an effect that appears when an object is measured. We measure a quantum object and in this way bring it into the real world. If we're talking about some event, then mathematics, higher mathematics, allows us to describe it through mathematical formalism. And quantum physics, as you know, is built on mathematical formalism. 99.9% of the effects we study in quantum physics were initially mathematical effects. And now it's worth emphasizing that both quantum superposition and the observer effect are, by and large, mathematical effects that were later discovered in practice. And quantum superposition is described mathematically. Superposition implies that there is a probability density distribution, and the most probable value will manifest at a specific moment. And then at some point, scientists had a sudden insight. They realized that if we have quantum objects that possess quantum properties, and there is a solid mathematical formalism for them, and we have this kind of probabilistic calculus based on probability densities and similar things, then perhaps it is possible to connect a quantum particle, a quantum object, with methods of working in mathematics with such entities. This is how the idea of quantum computing emerged. Quantum computing is based on the fact that essentially we take a quantum object, apply to it the effects we have described, and use it to obtain the answer to the specific result we are seeking. A quantum object that exists simultaneously in all possible states or in a state of quantum superposition is called a qubit. It is a particle that is in a special state where it possesses all possible states at once. When we have a superposition state, we need to somehow reveal it. For this, detection or measurement is used, or the observer effect manifests itself. And so, essentially, we can mathematically describe everything that interests us in the form of probabilistic logic, then measure it, and in this way obtain the answer. If the qubit is described mathematically, then all that's left for us to do is simply measure it. And all of this whole crocodile, which we would have had to calculate on paper, everything on paper, all these things to compute, we calculate in the blink of an eye. So things are not exactly going badly. We have a quantum particle. We have a mathematical formalism that describes all possible states. This mathematical formalism, in the ideal case, implies an answer that would otherwise have to be calculated. And this answer would be the selection of that state which, out of the entire probabilistic field, from the probability density distribution, is the most likely. And instead of calculating all this and performing these incredible cumbersome operations on paper or in some other way, we simply measure this particle and find its most probable state. That very act of measurement reveals, out of a million possibilities, the one option we are looking for. Now comes the most important part. We need to somehow prepare an algorithm so that it operates in a non-standard way. How would all this work in the usual case? We would use this running around with ordinary bits. We would use semiconductor systems in order to work with zeros and ones. And to write this kind of loop that would calculate probabilities, we would need significantly more space and ways of describing things than is possible with a quantum system. But a quantum system exists like that on its own. We don't need to repeat using zeros and ones from the possible states of a bit the huge amount of logic required to describe such a state. And the algorithm is based on this probabilistic computation. Perhaps I'm calling it by the wrong name. If that's the case, please correct me in the comments, but I think the main idea here is absolutely correct. And when we talk about this, we have the right to expect much faster computation since the particle exists in all possible states at once, and all that's left is to measure it, which is much faster than having bits that need to be switched or flipped. What I said about the algorithm is of course absolutely true, and this needs to be taken into account. Algorithms for quantum systems are written in a special way. Quantum systems can work efficiently on solving a certain range of problems. It is not practical to solve absolutely all problems on quantum computers, and as you can probably already guess, the kinds of problems that fit well here are those that involve some sort of probabilistic model. All tasks related to building probabilistic logic will be well suited for quantum systems. And then, this combination of measurement and superposition will continue to operate. This is exactly how a quantum computer functions.